Greetings and welcome to this video in our series on strength of materials and mechanics of materials. You might be wondering why I have a picture of a surgical situation here. Well, this particular example and analysis has to do with bending. If you'll notice, these are laparoscopic tools, and the surgeon operates them along with a camera that you can't see here, and actually does operations using video. And since their incisions here are very small, the recovery is a lot faster. But it requires a bunch of these tools. Now, these tools come in various sizes. This seems to be a 5mm instrument, but I have a 10mm tube example ready for us to look at. And here is an example of a 10mm tube. So it's 10mm OD, 9mm ID, 250 millimeters long, which is a little bit short for one of these, but they come in various lengths. And if you'll notice, I have a hole here. We'll talk about that later. Now, the surgeon operates it here, but it often rotates in this area, and down below inside the patient is where the actual work happens. So we literally have 1, 2, 3 places of contact, and sometimes this can result in a bending situation. The numbers are a little bit arbitrary, but I chose that the surgeon would be placing his or her force at this point, and the fulcrum would be here close to the surgeon's hand would be the patient, and deeper inside the patient at 200 millimeters would be where the reaction force would be. So we've got a reaction force on top and one on the bottom and an applied force here. And I'll write those down when we get to the workspace. An example of this tubing can be found at this website here. If you'll notice, we have some metric tubing, and these are intended to be medical grade. So this is the exact kind of thing that's used in this situation. So if you look down here, they have various sizes in millimeters, and they give the dimensions in inches here, but we're going to use this one, 10 millimeters OD, 9 millimeters ID. All right, here is our workspace, and I'm going to show you where the forces are. And we have force of 60 newtons applied here. That's actually a pretty heavy load, but we're looking at a worst case scenario here. We have a reaction force here at the patient and another reaction force down here. Let me give you the broad strokes of what we're looking for here. This tube is going to be under bending, and we need to do a full analysis of how much stress. And there are two main kinds of stress in this situation. One is flexural stress or bending stress, and that's a normal stress. It goes perpendicular to the cross section. So often we're considering that as a cross section. The bending stress or flexural stress is normal to that, and so it will be denoted with sigma. Now, shear stress also occurs, and that will be parallel to the cross section. So both of those are happening, and we need to calculate both of them. Finally, we will want to know how much it deflects at various locations. So deflection is an important consideration as well. So we are finding bending stress, shear stress, and deflection. Now, this particular example uses these formulas multiple times, so it's a good example for the student. Okay, so let's start off listing up what we're trying to find. I'm going to write that over here. So we're trying to find bending stress, and we're trying to find the maximum and also what it is at the hole. Okay, we're trying to find the maximum shear stress and also what it is at the hole. And for deformation, the lowercase delta, we want the deformation at the support, this one here, the maximum deformation, and also the deformation at the hole. Okay, let's put A, B, C, and just in case we want any other letters in between, I'm going to call this point Z, or Z for some of you elsewhere in the world. Okay, so these are the things we're trying to find, and we are given, first off, we're given the diagram. All right, so there's that. So I'm not going to write down those things, but we've got the OD of 10, ID of 9, length of 250, and I'm going to fill in some of these others. So from here to here, 50 millimeters, and this is going to be, of course, 200 millimeters, and from the hole to Z is right in the middle, 125 millimeters. Okay, so that's given here. Now we have this force of 60 newtons. That's also given. One other thing that's not given yet is, you'll notice they use type 304 and 316 stainless steel. We'll be using type 304. 304L as a matter of fact, but that doesn't change things that much. So stainless steel. Okay, now we've written down what we want to find. We've written down what we're given. And in order to find these things, we're going to need to use some of our favorite equations. First, in order to find the bending stress, or the flexural stress, we use our favorite equation, stress equals mc over I. To find our shear stress, we can use VQ over IT. Now this is the general shear formula, but we're going to simplify this in a little bit. So hold on to your hat before you use this. This can get a little hairy sometimes. Now in order to find these, notice that each one of these has a load. The M and the V both come from loading. C and I come from the geometry of the cross section, and same thing with Q and IT. And we relate the stresses to the material. So you'll always have in these types of problems a material characteristic, a loading characteristic, and a geometry characteristic. So we're not given a whole lot of these things, so we're going to have to figure these out. Okay, so for M and V, we are going to have to use our shear force and bending moment diagrams. And to find C and I, well, C is pretty easy because this is a tube. So C is going to be equal to outer diameter divided by 2. I, for a tube, is fairly simple. It's pi over 64 times the outer diameter to the fourth minus the inner diameter to the fourth. Now, if you've been watching my videos, you'll notice that J is equal to pi over 32 times this. And that's not a mistake. The area moment of inertia about the centroid is half of the polar moment of inertia about the centroid for a circular cross-section. Now, when it comes to the shear stress, I promised you something a little different. For a thin-walled tube, we can estimate that the shear stress is 2 times V, which is the shearing force, over A, the area of the cross-section. So all we need there is the area of a cross-section is pi over 4 times big D squared minus little d squared. So what we're really doing is we're simplifying for both of these, taking the total as if it were solid, that's big D to the fourth, and we're subtracting out the smaller inside diameter. Okay, so we know what we're going to use here. In order to get started, we need to use our shear force and bending moment diagrams. I'm going to draw the lines coming down from the beam here first, but I won't make you suffer through that for a couple minutes. Well, it's going to be hard to create this if we don't know what the values at B and Z are. So we'll have to use some of the moments about points B and Z to make this work. Now it's going to be 60 newtons times 50 millimeters. And then ZY times 200 millimeters. ZY is counterclockwise, 60 newtons is clockwise, so we get ZY equals 15 newtons. Some of the moments about A equals 0 equals 60 newtons times 250 millimeters. That's also going to be clockwise, plus BY times 200 millimeters, and that's going to be counterclockwise. So you end up with BY equals 75 newtons. Since I assumed that it was going down, that means it must be a negative 75 newtons. So if we add these up using some of the forces, then 15 plus 60 equals 75, and they all cancel out, so it all works out. Okay, so let's go fill that in. That's 75 down, and this is 15 newtons up. Okay, so now we can construct our shear force bending moment diagram. Let's make some lines down here. Now the pattern here is that it's going to go up straight, and then there's no load here, so it goes across, then it comes down here, but that was 60 here. This comes down 75, so it's going to be negative 15 here, and then continues across. Okay, and the areas here are going to be 60 newtons times 50 millimeters is 3,000 Newton millimeters. And if you do negative 15 times 200, you'll get the same thing. A2 equals negative 3,000 Newton millimeters. Okay, to finish off with the bending moment diagram, that becomes fairly simple. It steadily goes up linearly, and then it goes down in the same fashion with a height of 3,000 Newton millimeters. So now we can safely say that the maximum shearing force is 60 newtons and our maximum bending moment is 3,000 Newton millimeters. Like I said, this is a fairly simple setup, and it will serve us well for the rest of the analysis. Okay, so we have still yet to find, well, we're trying to find the stress at max and the stress at the hole. So let's do that. Let's use our equation mc over I. Now we found our maximum bending stress here of 3,000 Newton millimeters. And C is half the diameter right here. That works out really easily for circular cross sections. So D over 2, D is 10, so this is 5 millimeters. And then I, so that's pi over 64 times 10 millimeters to the fourth minus 9 millimeters to the fourth. And we end up with 88.9, let's see what our units are up here, Newton, millimeter over, well, this thing comes out to millimeters to the fourth. And so we cancel, there are 4 millimeters on the bottom here, 2 up on top here. So we end up with Newton per square millimeter, and that is in megapascal. Okay, and that's the maximum stress here. And that occurs right where that 3,000 Newton millimeters is, right here, this point where we have the reaction fulcrum of 75 newtons. And that's not surprising. Okay, well, getting back to the hole, you're probably wondering why I put that in there. Well, bending members are rarely consistent all the way from one side to the other. There's always something that someone wants to put in there, or add in, or take out for whatever reason. Now, often these laparoscopic instruments do have various things, usually at the end, but I'm throwing this one in the middle for ease of the example here. So I'm going to use that same equation, stress at C, or the hole, is, again, mc over I, but the moment is different. It's not this maximum bending moment, it's whatever that is going to be at this location here, 125 from the end, or for that matter, 75 from B. So we have to figure out what this value is right here. Now that value is part of a linear slope. So it starts at 3,000, ends at 0, and we know the distances, so we can figure that out. MC is, well, the top is 3,000 Newton millimeters, and the bottom is 0, so we don't have to worry about that. And it's simply that fraction of it. So how far up did it go? It is up 125 from 0. And the total is 200. So it is 125 200ths of this value. If we got all the way from 0 to 200, it would be 3,000. If we were at 0, it would be 0. So it's this fraction of 3,000, which is 1875 Newton millimeters. Okay, so let's plug this back in. We've got Newton millimeters times C. That doesn't change, and neither does I. So that's easy. 5 millimeters. And maybe we should have calculated I ahead of time. It's usually a good idea. Pi over 64 times 10 millimeters to the fourth minus 9 millimeters to the fourth. And we end up with 55.5 megapascals. We could have used the same ratio to simply change our stress, but I wanted to show the use of this equation one more time. Okay, next question is though, why do we have to find that stress at the hole? Well, if you take material out of an area, that's going to increase the stress on the rest of the material at that area. So the actual stress is going to be higher than this, but we're not going to consider that stress concentration in this particular video. But it's good to know what it would normally be without the hole at that location, because that would be the first step in getting a more realistic answer. It's going to be much higher in that area once the hole is taken into consideration. The next step is to find the shear stress. So tau max. We're going to use this 2V over A. So that actually makes it very simple. VQ over IT can be, like I said, kind of difficult, but this makes it very simple. And this is an approximation, okay? So it's approximately 2V over A, which is 2 times, well, we're talking about the V max here, and so that is right here, 60 newtons. And the area is, well, let's calculate that out. Area equals pi over 4 d squared minus d squared, and that comes out to 14.9 square millimeters. Okay, and that yields 8.04 megapascals. Okay, now we're going to find the same thing at the hole, or point C as it's noted. And again, it's approximately 2 V over A. This was V max, whereas this is going to be V at the hole. And we have to look at it again the same kind of a way, that we have to find what the shearing force V is at that point. But this is really easy because it is a flat line all the way across. So whatever it is over here, and in between, it's 15. Don't have to worry about the negative because we can use the absolute value. And the area, 14.9 millimeters squared. And you can practically do that one in your head. We end up with 1.005 megapascals. All right, so we are well on our way. We were supposed to find the stress maximum and at the hole. We did those. The shear stress maximum and at the hole. We did those. Next, we need to look at deflection. Okay, in order to find the deflection at any point along this beam, we're going to need to employ some charts and tables from some source. Now, I use a couple of different books, as well as a great resource is the AISC, or American Institute of Steel Construction handbook. It has all sorts of great references for this type of thing. For this one, I'll be using a textbook that I use a lot, and the information for that is on the screen. These tables look something like this. Okay, so you have a diagram here of the loading and the setup and so on. Well, the equations are here. These are similar to what I'm using, but not exactly the same. This diagram really isn't all that great because it's not all that clear what's what here. These are the formulas for various loads and angles and deflections and so on. And this is what our setup is like. Simply one support on either end with a load down the middle. Same basic idea, even though this looks like you have to have an applied load here, you could have the applied load here, and as long as you know what those forces are, you're all set. Okay, so I'm going to relay the formulas from my textbook to here. And they do get a little bit complex, so bear with me. So we're trying to find the deflection at the 75 newtons. It says the support, but what we mean by that is at B, and the maximum and the whole. Let's start with the maximum. And it's actually one of the more complex ones here. It's P, which is the load here, 75 newtons, times A times B. Now, what is A and B? The one that I was using considers things going from right to left. So A is going to be the 200 millimeters and B is going to be the 50 millimeters. Now I'm going to rewrite all those in a little bit, but those are two lengths. Speaking of length, L is the overall length. And then you multiply that times the square root of 3 times A, and then you have that L plus B thing again. And you divide all that by 27 E times I times L. Well, let me go through this a little bit. This equation, first off, where does it come from? It comes from a derivation based on calculus and differential equations. It does look a little bit complex, but you just need to be careful of how you plug things in, and then watch out for your units as always, and it doesn't end up too bad. What I find is very, very helpful is to simply start making a list of everything. So I say P is 75 newtons, A equals 200 millimeters, B is the other side of that, it's 50 millimeters, L is the total length of 250 millimeters. E, well, we never looked that up, so under lookup, E of 304 stainless steel is here, where we've got this 304 stainless steel from a common supplier. They give you a lot of information here. But let's go here. We've got modulus of elasticity, anywhere from 28 to 29,000 KSI. I usually use 29,000 KSI for the modulus of elasticity of stainless steel, and 30,000 KSI for less alloyed carbon steels. So we fill that in for the modulus of elasticity. Well, from before, we were calculating I, but we were just throwing it into an equation as part of the formula. So we should calculate it out here. Pi over 64 times d to the fourth minus little d to the fourth, and that ends up with 168.8 millimeters to the fourth. Okay, I think we've got all the factors. P, A, B, L plus B, 3ALB, 27EIL. Okay, so we've got all those factors here, and just need to plug them in. 75 newtons times 200 millimeters times 50 millimeters. Open that up. L plus B, we can just do that right here. That's 300 millimeters. And take the square root of 3 times 200 millimeters times 300 millimeters. Put all that over 27 times 29,000 KSI times 168.8 millimeters to the fourth times 250 millimeters. I don't know if you noticed the big problem that we ran into here, but here it is. If all you do is pick up a number like 29,000 and you don't bother to really notice what the units are, guess what? You'll be in big trouble. This is the value in US units, not the value for SI units. So we need to find out what that is and use instead 193 to 200 gigapascals. So we'll use 200 gigapascals. Okay, now that we've got that taken care of, we just need to calculate this all out. We get 419, and the units are challenging here. Millimeters, 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 square root of millimeters squared, all over gigapascals times millimeters to the fourth times millimeters. And don't forget newtons at the very beginning here. So to cancel out, we've got 1, 2, 3. This square root of millimeter squared is a millimeter. So 1, 2, 3, 4 cancels out with 4 millimeters on the bottom there. And this gigapascal is actually 1,000 megapascals, and a megapascal is a newton per square millimeter. So I can, from there, cancel out newtons on top and newtons on the bottom. Now this millimeter squared is on the bottom, bringing it up on top. So since we've got millimeter squared on the top, I can cancel that out with that, and we end up with just 419 over 1,000 millimeters, or 0.42 millimeters. Okay, that is our maximum deflection. Where is it located? Well, there is a formula for that too. It depends on the geometry and where the load is and so on. So we need to use this formula. X1 equals square root of A times L plus B, all divided by 3. And that's the square root of 200 millimeters times L plus B, 300 millimeters. All of that divided by 3, and that's at 141 millimeters. And that's from this right-hand side here. Like I said, the chart I was using kind of goes more from right to left. So at 141 millimeters, somewhere, say, around here is x1. Okay, so we found the deflection and the location of that deflection as at the maximum. The other ones are a little bit easier. So y at the load, or the support, we'll just call that point B, equals P A squared B squared over 3 EIL. Notice how EIL comes up here and here. In fact, EI is the stiffness of the beam, and it's always going to be included in these calculations in this way. So it might even be helpful for you to calculate EI or EIL ahead of time and save yourself some calculation troubles. And you can also calculate the stiffness and compare that with other possible setups. All right, so continuing on, we have 75 newtons times 200 millimeters squared times 50 millimeters squared. Now notice how the square applies to the whole thing. I usually write a little bit higher. I could put things in parentheses, but it gets a little bit messy that way. You should probably put it in parentheses if you've got an exam or something. 3 times 200 gigapascals, we'll use the correct one this time, times I, 168.8 millimeters squared, times L, 250 millimeters. Okay, and that comes out to 0.30 millimeters. So as expected, it's less than the maximum, and we know exactly where it is. It's at B. So we're good with that. And then y at the hole, which is C, is PBX over 6 EIL. But that gets multiplied by L squared minus B squared minus X squared. So P 75 newtons times 50 millimeters times, now this X thing, we have yet to figure out what X is. We never put that in up here. So X is where the hole is. And like I said, it's going from right to left here. So that would be 125 millimeters. So X is 125 millimeters. And that's all over 6 times that EIL thing. And then there's this L squared minus B squared minus X squared. So we'll have to bring that down to a new line. B is 50 millimeters. And again, X is 125 millimeters. And all is said and done, that comes out to 0.41 millimeters. And that's not that surprising because that's where X is 125 millimeters, not too far from the 141 millimeters here. So we found the deflection at the support, 75 newtons, point B, the maximum deflection, we found out where it was too, and at the hole, which is point C. So our maximum was 0.42 millimeters, 141 millimeters from the right. At the 75 Newton force, the deflection was 0.3 millimeters, and at point C, the hole, it was 0.41 millimeters. Well, this was kind of a long problem with all the things that we were trying to do, but as long as you set it up well with all of your things that you're trying to find, with all of your givens, with all the things that you look up, and you just keep at it one step at a time, you can solve these types of problems. So to summarize, we started off with a surgical tool that was in bending, and we assumed some geometry and some loading and solved for the reactions and found our maximum shearing force and the shearing force along the beam, as well as the bending along the beam. For what we were using, we realized that we needed to find these things as well as use some of these other formulas. Employing those formulas yielded the bending stress at two different locations and the shear stress at those two locations. That was fairly straightforward. We also, very importantly, used an approximation for the shear stress because it's close but not exact. But it's much easier to calculate than using the general shear formula. Continuing on, we needed to calculate the deflection at three different locations, one of which we didn't even know until we were able to use a formula to calculate that. So we obviously needed a little bit more space. We needed to look up the modulus of elasticity of the 304 stainless steel, and we found it was very helpful to just list all the different parameters first and then employ the formulas and then actually calculate out the formulas. One thing to note were that the units, always have to be careful with them. In fact, we looked up the wrong modulus of elasticity, but figured it out pretty quickly because we actually wrote down what we were doing, that KSI was not going to work very well with the millimeters and newtons involved. We were able to calculate those deflections at those locations and solve the problem ultimately. Well, I hope this has increased your understanding of beam stress and deflection, and that you will continue to improve your knowledge and skills using these videos. I look forward to your feedback and your continued watching.